Welcome back. Polls, polls, polls. Sick of them yet? Well, they're a tool born out of this unit's lesson. If you've ever read polling results, especially during election years, you'll note that they provide the results of the sample along with some margin of error, which is the mean, give or take some amount. This range of values forms what we call a confidence interval. And it is our first attempt at inferential statistics, in which we go beyond just describing the sample, and instead we draw inferences about what is in the population from which the sample was taken. Now, in 20 plus years of teaching this subject, the question I have been asked the most is, how large of a sample do I need to do blank? The answer will surprise you, as it is less than you think. After all, while a sample of 500 people chosen randomly from a school with 2,000 students may seem acceptable, but not great, a sample of 500 chosen from the entire state population that's in the millions, or from the U.S. population of 300 million, are equally good. How's this possible? Well, step right in, and all will be made clear to you.
Welcome to Unit 3. In this unit, we're going to address confidence intervals and sample sizes. Before we get into either of those computations, it really helps to give a stronger background on sampling in general, because it's from sampling that we actually are going to do a lot of this stuff. This truly is where inferential statistics takes form. Earlier, we discussed the use of samples to get statistics, whereas with populations we had parameters. And I had asked why on earth we would want to take a sample, and why not take the entire population? Well, here we can actually see why. One reason I mentioned earlier, cost. If you actually tried to survey every living, breathing person on any issue, it would cost way too much. By the time you actually finished doing your survey, you would be broke. There's no way you could survey every living, breathing American on any issue, nor would you even want to try. So yeah, the price would be too prohibitive, and the time involved, I couldn't even imagine if it's even possible, to have enough time to do that, to track everybody down. Well, you know that every 10 years when they do the census, they have to go hunt people down, knock on their doors to go find them. And there's people who are homeless, on vacation, on cruise ships, in the military, in the hospital, that they have a really difficult time finding. So you have the issue of the time it takes to get them, and the fact that many of them are just not easily available. Heck, there are people, if you tried calling them, they might be home and just refuse to answer their phone. Can you possibly imagine people refusing to answer their phone to talk to a pollster? Gee, who'd have thought? There are other reasons, too. One that most people have questions about when I tell them is the accuracy one. The fact that I consider samples to be more accurate than populations. Now, it sounds strange. Why would it be more accurate to have part of a population than to have the population? Well, that's assuming you actually have the population. See, it's one thing if I say get the population of all of the stock prices from the New York Stock Exchange. You can go on the internet, download it in an instant, and you've got it all. And I have very little doubt that you've got the entire population. Load it directly into Excel, and voila, you can do all your number crunching, and I would trust that you truly have parameters there. But try to do a survey on people. Do you really believe that the census captures everyone, not leaving out a single homeless person, a single comatose person, a single person in the mountains on vacation or whatever? Because if you're missing even one, then you don't have a true population. And part of the problem is we always react like we do. So when they report the results of the census, they say, this is the truth. This is the real average of whatever it is, salary, ages, or whatever it is they're reporting. Whereas when we take a sample, we know it's not perfect. We know that there is some margin of error, and we report it that way. So we'll say the age is X, give or take a couple of years or whatever. We build the error into our analysis. So I'd feel much better about hearing the average give or take with a degree of error that's acceptable versus saying, this is it, it's the truth, it's the whole truth, and we're sure of it, when I'm frankly not so sure of it. And the last reason why sampling is often superior to populations is something that doesn't apply to all cases. It's what I call destructiveness of observations. The very practice of taking a sample often involves destroying or consuming that which you're testing. Now, that doesn't happen with everything. I mean, you survey a person, it doesn't kill the person, although you'd wonder that sometimes the way people act. But when you do something like testing a battery, if you put the Energizer batteries in those little pink bunny rabbits like they used to do in those commercials, and then time them until the bunny rabbit stops working, and say, this battery lasted 273 hours, that's great, get all the data. If we said we don't want a sample, we want the entire population, you would have to test every single battery we make in all these bunny rabbits so we can get accurate data. Only one problem. You won't have any batteries left to sell. And what good is that if your business is to make money and you won't have any product left? And likewise, if I said we make Famous Amos cookies, and before we will package our cookies, we have these taste testers who will take a bite of the cookie before they put it in the package. And if it doesn't taste good, it gets thrown away. But if it does, they put that partially chewed cookie back in the bag and put an inspected by number 3 on it. Obviously, no one's going to want to buy a chewed cookie, even though it has met the mark of quality. So yes, you will have to destroy that which you're selling, and it's not practical to have to test everything. So between time, cost, accuracy, availability, and potential destruction of observations, we have many good reasons to take samples. So we know we want to take samples, which really is the essence of what we do in statistics. What do we do first? Well, there's really 6 stages we go through when it comes to selecting samples. The first step is to find the target population. That's the group that you're really trying to study as a whole. When election polls are done, especially during presidential election years, they're not polling people who are not likely to vote. They're not polling people who aren't U.S. citizens. They're not polling high school students. They're polling potential voters. They want to know what people are actually likely to vote. That's why they'll go after people from voter registration records and find out who has voted, because your opinion is weighted more heavily than someone who may have registered and never votes. So they want, what group are we trying to represent? They're not trying to represent America. They're trying to represent the American voter, because that's the people who actually determine who the real winner of an election is. So you define the target population that you're trying to represent. The second step is to select a sampling frame. The sampling frame is just the source from which we get the sample. It could be something physical, like a phone book or a mailing list, but it could also be situational, where you say, I'm going to survey people based on the fact that they were standing in line at the Starbucks during the morning rush hour, and I want to sample people who happen to show up that morning. So sampling frame, like I said, it's either the document itself or something, with names on it, or some situation, as they said, that you're pulling from. Heck, if I just had everybody take their name tags and throw it in a pile and I draw the sampling frame is the pile of name tags that happens to be there. But the phone books are probably the most common ones we think about. So you pick whatever your sampling frame is. Now you have to consider the sampling frame. Don't expect it to be perfect. It doesn't have to have every possible member of the population in it to be a good sampling frame. And it's not a percentage thing. It's not that it had 99.8% or something like that. You have to ask yourself, would the results be different had I, from the population, if I'd used something else, or do I expect the results to be dramatically different, significantly different? You just want to know, is that sampling frame resulting in error that you otherwise would not have expected to get? So, if asked, is the phone book a good sampling frame to use for a poll? And the answer, I know I often hear people say, well, no, because it doesn't have everybody. No, it doesn't, and it never will. And I don't care what sampling frame you use, chances are none of them are absolutely perfect. There's usually some error because somebody just left the company, somebody just joined the company, or whatever the case may be. But if I used, the real answer to the question, can I use the phone book, is it depends. Depends on the question being asked. If I were to use the phone book to find out, for example, what the professions of people are who live in our city, that's a bad use of the phone book. Why? Is because certain professions are almost always unlisted. You're not going to find judges, you're not going to find police officers, you're not going to find doctors. They usually have their names unlisted from the white pages for a lot of reasons. They really don't want to be bothered at home, or sometimes it's for safety and security reasons. On the other hand, if I use the phone book to call people and ask them, what's better, smooth or crunchy peanut butter, the world wants to know. Now, you have to ask yourself, do you really believe the results are any different because you use the phone book? As though, well, we used the phone book and got 63% who liked it smooth. Well, but there were unlisted people, and we know unlisted people tend to like it crunchy. I mean, do you really believe the results would have been different had the unlisted people been included? I'm sure it might be slightly different. It's not an absolute perfect one-to-one representation, but do you believe it's really significantly different? Do you believe the essence is that it's pretty well captured the results close to the accurate, even though it's missing those people? Chances are you should feel fine about it for asking for questions like peanut butter. So the phone book suddenly is a valid sampling frame. So it does depend on the situation. So now you've chosen your sampling frame, whatever it might be. Now you have to choose a sampling method. We have two categories of sampling methods, what we call random and non-random samples, or they call them probability and non-probability samples. Whichever works for you, books just use them interchangeably. Amongst the non-random, non-probability samples, there are several different possibilities. The most well-known is something called a convenience sample. It's also known to most lay people as a mall survey. This is the sample in which you basically have that person with the clipboard annoying the heck out of you while you're going up the escalator to the food court, and they will chase you down until you tell them your favorite brand of laundry detergent. They're choosing you because you're there. Not that you were random, but you were conveniently there. Is that data biased? Absolutely. Basically, it's biased toward the people who would be at the mall. You're not going to typically find lower income people. You're not going to typically find higher income people. You're not going to find people who are working during the day. You're finding a select group of people. It's very biased for sure. And then these people who are doing the polling don't just stop anybody. They stop people that they feel they can stop. They don't feel intimidated by. You're not going to see these mall survey guys stopping a couple walking hand in hand, or stopping a 6'6" guy who looks like a linebacker. But they will gladly stop a woman pushing a baby stroller because they know they can outrun them. So the data they collect from them, hardly representative. Is it any good? I wouldn't deny that it's useful, but it's not representative. You cannot take the results of such a sample and project it up to a population when it's not random. You can certainly say, of the 50 people I stopped, 40 said blank. That's fine, but you cannot say, therefore 80% of the population feels that way. So such is the problem with a convenience sample. They're definitely quick and easy to get, they're cheap to get, but the data is typically not really valuable. Another type of non-random sample is what's called a judgment sample. This is one where experts choose the sample for you. They use whatever is at their disposal. It could just be their opinions, it could be historical information. Two of the most famous judgment samples are the Consumer Price Index and the New York Stock Exchange's Dow Jones Industrial Average. The Dow is based on the prices of 30 stocks from the New York Stock Exchange added together and then multiplied by different numbers through some formula. And the Consumer Price Index is basically adding the prices of items that they consider to be common items in the household, commodities, this particular loaf of bread, this particular orange juice, this particular milk, and so on. So experts decided what goes into it. Could they be wrong? Absolutely. Remember back in 1999 when the stock market crashed, the entire market didn't crash. The Dow did, but not the whole market. What really made it look like that was that of the 30 stocks on the New York Stock Exchange's Dow, 14 were high tech. And when you have 47% of the Dow being high tech, and the dot-coms became dot-bombs, and the crash was almost exclusively a high-tech thing, it certainly made the Dow look pretty bad. So, a judgment sample can be destructive when their opinions actually turn out not to be good. but for the most part it's worked very well. A snowball sample, that's one where a sample just seems to snowball. It just gets bigger and bigger and bigger. You tell two friends who tell two friends and so on, that kind. That often is prompted by the kind of questions being asked. If a president of a company decides to sample a few people and ask them whether or not they would like a pay raise this year or to forego that pay raise so we could reinvest money into the company for future growth. And suppose they said, well, we just want to get a sample of 100 people. And if they said, we just want these 100 people to just call us, and they sent out emails to 100 people and said, please call and give your vote. Well, you could bet those 100 people will probably tell another 100 people who will tell another 100 people, and before you know it, they'll get 1,000 responses to their 100 questions. Because these people don't want to lose their pay raise, so they're going to make sure their opinion counts more than once. That happens when people think something is really important. Sometimes they do it just because it's silly and fun. You'll see people voting on stuff on the web that's not very important, but they think it's fun, so they forward it around. But in general, snowball samples where you start out with something initial and it just grows and grows and grows. And then a voluntary sample, that's one in which people throw themselves into the study without an invitation. Something is posted, anyone like to participate, just vote. The most common ones we hear about nowadays is American Idol. People vote on American Idol just because. You see the phone number on the screen or go on the website or whatever and you vote. No one asked for your vote. You're giving it voluntarily. So there's a difference between you being selected to vote and you selecting yourself to vote. And we can't limit how often you vote. So how much can we really trust these results? It's totally non-random, and people who are passionate about something probably vote many, many times on the exact same poll if it's something that they consider to be really critical or fun or whatever it is. You will see that happen sometimes. That covers the non-random samples. Let's look at the random samples. The most basic one of all we refer to as a simple random sample. Basically, lotto. You think about it, 50 some odd numbers on balls in a machine mixed around, 6 are randomly drawn. That's a simple random sample. Shuffle a deck of 52 cards, deal 5 cards to somebody. That's a simple random sample. While it's called simple, it's not really, because it takes a lot more work to draw that sample than any of the other ones we're going to talk about, because each one is selected separately. If I wanted to take a random sample of, 25, I have to select 25 one at a time. Whereas in a systematic random sample, you only have to pick one and everything else just kind of falls in place. I could turn around and say, well, everybody in the room stand up and call out numbers, 1, 2, 3, 4, and so on and so forth. And I could say, okay, here is the deal. I'm going to flip a coin. Heads, all the odd numbers stand. Tails, all the even numbers stand. I have just then sampled 50% of the class with one coin flip. So that's a way of systematically choosing my sample. And what makes it random is that everyone has an equal probability of being selected, which they would. A third method is called a stratified random sample. That's basically where we stratify the data into subgroups, and then we randomly choose within each subgroup using whatever method we want. Suppose we had a group of 100 people, and in that group we had 60 men and 40 women, and of the men and women we have so many business majors, so many educations, so many nursing majors, and maybe within each of those subgroups too, we might say, well, we have these people are freshmen, sophomores, juniors, seniors. You can go on and on and on. Let's just stick with gender and major. Well, we might say, well, there are, of the 100 people, 20 are females in education, and 10 are females in business, and so on and so forth. Now, of these 100 people, suppose I wanted to randomly pick 50. Just randomly picking 50 as a whole, it's possible that an entire subgroup might get omitted or be overrepresented even. It's possible. But if I say, well, there are 20 women in education, let's put them over here in one pile, and let's randomly pick 10 of those 20. However we pick them, whether we do it in a simple method or systematic, it doesn't matter, but we randomly pick 10 of those 20. And then we have 10 men in nursing, and we randomly pick 5 of those 10 using whatever method we want, and so on and so forth. By the time you're done, you've got your 50, but you've got all the subgroups well represented at the same time. And that's called stratified random sampling, since we're sampling the groups in strata, in layers. The last random method is a cluster random sample. Essentially, that's where you randomly choose an entire subgroup at once, and then all members of that subgroup are automatically picked. So if you have a university where there are, let's suppose, 50,000 students at that university, and you have classes are, let's say, 25 students per class that's meeting any given time. So maybe there's let's say 500 different classes being offered this semester. And, some courses, some students are taking more than one course. Let's say there's 500 courses being offered this semester. I want to randomly survey, let's say we wanted to only capture 250 people. Now there's 500 courses, there's 50,000 students. How do I get those 250 students? Sure, I could turn around and mail 250 out, but good chance some of them will get thrown out, never turned in, who knows. What if I went and randomly pick 10 classes and then walk into those 10 classes and survey all 25 at once? Now think about what you get there. You get the 250 you've wanted. You did it randomly, but instead of randomly picking the individuals, you're picking the groups at random. So you're getting your data quickly. Chances are they will all respond to you. Walk into a classroom and say, will you do my survey? 99% will say yes. Mail it to their home. You're lucky if half of them don't throw it away. So you'll get quicker response time. You'll get better responses. You will represent the overall population as long as the sample is decent sized enough. I wouldn't just pick one subgroup and say, there, I'm done. But if you decided to do several subgroups like that, yes, you would be. So you would find a way to reasonably accurately capture the population. Not quite as well as the other methods, because it's possible you pick a few subgroups. You might just pick an oddball subgroup that you happen to leave out all freshmen or something like that. That can happen. Not likely, but it can happen. So we've covered the different sampling methods, whether it be random or non-random. Next, you would determine the sample size. We'll be getting to that later in this unit when we cover sample size computations using Excel. So we'll just skip that for now. You choose a data collection technique. Do you want to do it in person? Want to do it on the phone? Want to do it by mail? Want to do it by email? You pick whatever method you're going to use, and think about the fact that they have their benefits and their costs to them. The cost of actually doing a survey by phone is very expensive. By email, it's extremely cheap. You can send out so many at once without paying a nickel. The time required, doing it by mail takes a lot more time than going, in person. Still takes some time. Email, very little time. How much data can you expect to get? Well, in person, you can get a lot more data because you've got them right there, and you can take notes. Email, some, because you can have attachments. Mail, you're a lot more limited. So when you go through all these different reasons and then make your decision what's available to you. After you've gone through all this, last step is to actually select your sample. So we've collected our sample. Now what do we do with it? Well, the intent of getting the sample is to learn about the population. And one of the best tools out there is something known as a confidence interval. Confidence interval essentially is, it's taking the sample and saying, let's estimate what the population value is, what the mean is or proportion is of the population, and then, for good measure, add in a margin of error because we know it's not perfect. When you're taking data from a small group and trying to tell what the truth is about the large group, I don't expect it to be dead on accurate. So you create what we call a confidence interval, which says, I believe the truth is what the sample shows, plus or minus some margin of error. To try to help understand that concept, try to picture this. Imagine if I had everyone in the room close their eyes. except for one person. One person, he's got a beanbag in his hand, so he's going to throw it and aim it at a target. I'm going to flash a target on the front wall. He takes the beanbag and throws it at the target. And now I turn the lights back on again, and the target is no longer there. So remember, I lit the target up on the wall. Only he could see it. Everyone's eyes were closed. Now the target has disappeared. Everyone's eyes open. But all you can see is where his beanbag hit the wall. And I said, okay, take a look at that mark on the wall. Guess where the target was. Now, instinctively you would say, well, it's probably somewhere near the beanbag. And that's probably a good guess. How far from the beanbag might it be? Do you expect it to be really close, really far away, or who knows? Well, that depends on a lot of things, not the least of which is how good is his throwing arm? This guy might have absolutely no ability to aim at and hit a target. This guy might be dead on accurate, and he might have nailed it. We have no way of knowing. But the only guess we have to go with is where he actually hit it. So are you going to trust that that's the correct target that he was aiming for? Probably not. But you're going to say, let's start with that and then give ourselves a lot of room for error. Turn off the lights, flash the target on the wall, have you close your eyes again. He throws a second beanbag. Except this one, let's say it hit 5 feet to the right. So now you got these two marks on the wall 5 feet apart. Turn the lights on, target goes away, and I say, okay, now where do you think the target actually was? And you're going, okay, he didn't hit the same spot twice. Maybe he had it the first time and his second throw was off. Maybe he missed the first time, he corrected himself, second time he nailed it. Maybe he missed both times. And he's missed it to the left, missed it to the right, but the point is, he got them 5 feet apart, so if I had to guess, I would guess somewhere in the middle, but I'd give myself still a decent amount of room for error. Put a big circle around that area. Suppose I had him throw it 10 times like this, and then you take a look and you notice that all the hits are relatively close together. So 10 marks on the wall, all within a really small area. You're going to say, considering that he keeps hitting that same area, I'm going to guess the target's somewhere in that area, probably not that far off, because he keeps hitting that area. The more throws he makes like that, the better you feel about it being in that area. Well, essentially what you've done is create a confidence interval. By the way, to try to imagine this realistically, imagine if you were standing in a war zone and try to think back, you're in World War II, and a Japanese zero-sen pilot's flying overhead, and he takes a bomb and he holds it outside the cockpit and he just drops it. He's trying to hit a factory, a bridge, whatever. It drops, something explodes. Did he hit his target? Well, we know he'll be back tomorrow unless he hit his target. Did he hit it? How far off is he? I don't know. What was he aiming for? Well, let's see. The next day he hit something else. The next day he hit something else. If I said, guess where the target is, your guess is based on where he actually hit it up to that point. So you're going to take the spray of shots and say, I think the target's somewhere in this area. Give or take, 50 feet, 100 feet, a half mile, whatever. Once again, that's a confidence interval. How large is that confidence interval? Well, it's based on a couple things. It's based on, for example, how much data you have. A person only throws once or twice, you don't have much to work with. The more data that person has given you, the better you feel about it, and the closer you think you're going to get to actually picking the right target. So larger the sample, the tighter the interval. Also, how confident are you trying to be? If I said, tell me where the target is with absolute 100% certainty, you're going to give yourself a lot of room for error and say, okay, the target is somewhere in this city. You don't want to be wrong. If I say you need to just be 95% sure, well, you'll allow yourself a chance to be wrong 5% of the time, so you're willing to make that target even smaller. If I said you only have to be right 10% of the time, you may as well pick a spot that's, 2 square feet. It's not as important that you nail it exactly because you don't care if you're wrong. So the more sure you need to be, the larger the target is. So that's how confident we want to be. We call that our confidence level. The higher it is, the bigger the interval is going to be, the more of a margin of error you're going to have to give yourself. And the third factor is his accuracy. If he's a very consistent thrower, hitting the same spot consistently, you feel a lot better, and so you're willing to put the projected target in a small area. If he's all over the place, you're going to have to give yourself a lot more room for error. So the spread of the data is a factor too. So when we actually look to compute a confidence interval, when we're dealing with traditional word problems and whatnot, we need similar information. If I say, what do you think the average age is of a group of people? You took a sample and you computed the average from that sample. What do you think the true population average is? Well, we'll start with the sample average. Use that as our starting point. And then I'll say, give or take what? And the give or take is based on, once again, 3 pieces of information. If I want to be 95% sure, definitely need more room for error than 90, less room for error than 99%. And what's the spread of the data look like? If it's very, very tight, don't need as much room for error. If it's not, need a lot more room, and I'll explain that in a second. And how much data is it based on? So we might say, well, the average age is 40, give or take 2 years. And if I took a larger sample, it might be 40, give or take 1 year. Now, to help you understand why that spread makes a difference, we measure the standard deviation. Why does that spread matter so much? Like, if I were to teach a daytime class of traditional age students, 18 through 22, and I teach a nighttime class of adult students who work during the day, probably no one in there younger than 25, some of them are in their 40s and 50s. And I said, okay, I teach 2 classes. Guess the average ages of my students in each class. And you say, well, give me a hint. I say, okay, I'll call out to you the ages of 5 students at random from my day class. I said, okay, here you go. 19, 20, 20, 21, 20. Guess the average age. And if I said guess the average age within a year, you'd say, well, I'll guess 20. And you'd probably nail it. Good chance that you would be within a year, that it's probably somewhere between 19 and 21 based on what you heard. The spread is so tight, that was an easy question. Let me give you my night students' ages. 25, 43, 58, 37, 49. You feel like yelling hike, don't you? You might say, well, the average is 44.7. Okay, can you give me within 1 year where you think the average actually is based on that sample? You're going to go, no way. They're all over the place. Yes, you can compute an average, but there's such a large spread that if I said guess within a year, you wouldn't feel comfortable. Heck, you probably wouldn't want to guess within 5 or 10 years with that spread. You might deal maybe 10 to 15 you do, but you're going to need a lot more room for error. So what could I do to make you happier? Give you more data. More data I give you, better you feel about figuring out that average within that margin of error. So you can see the standard deviation or the spread of the data makes a difference. How sure you want to be makes a difference, and how large a sample you take makes a difference. In the confidence interval Excel file that you have on in the course, I have a tab there for means and another one for proportions. Let's look at the one for the mean. You see there it asks for a standard deviation, which is that measure of spread we're talking about, a sample mean, a sample size, and a confidence level. And the part below, the finite population size, well, forget that for now. And below that, you see a bell-shaped normal curve, what we discussed in our prior unit. Well, based on that information that was given, we compute the average, which we already know is 550, the give or take. We call it a margin of error or sampling error. And on the spreadsheet, you see it says 550 plus or minus 41.278. The 550 is the estimate from the sample mean, and the 41.278 is that margin of error based on those 3 pieces of information. And if I were to change any of them, it would change this number. So if I wanted to be more confident, that 41.278 would grow. If I wanted to be less confident, it would get smaller. If I took a larger sample size, that number would get smaller, and a smaller sample size would make it bigger. And the standard deviation. If that standard deviation was smaller, sampling error would get smaller. If it were bigger, sampling error would also get bigger. So it's taking that information and says, okay, I believe the true population mean is somewhere between 550 minus 41.278 and 550 plus 41.278. And so it shows up there as somewhere between 508.722 and 591.278. It's saying it's between those two numbers. Not that the data is between those two numbers, but that the true population mean is somewhere between those two numbers based on the information given. That is our confidence interval. We are saying, I am 95% confident that the true mean is in that range based on the information we have. Sometimes your population has a limited size. You see, we are assuming unlimited population. It could be millions, billions, it doesn't matter. That's our confidence interval. However, in the event that you actually have a finite population size, a limited one in size, like in this example, there's only 1,000 in the population to begin with. Well, put it in there. What that will do is it will cut into your confidence interval and make it a little bit smaller. Maybe make it a lot smaller. It can't hurt it. It can never make it bigger. If I put in, 1 trillion for a population size, the interval would have been 508.722 to 591.278. It'll never get larger. But the smaller the population is, the tighter the interval will get. So think about it. If I had a population of 26, you've already got a sample of 25, which means you know the truth about all but one. You're only missing one person. That last person you're missing can't really hurt the average that much from what you've already gotten. So your confidence interval will be really small because you're so close. You got 25 out of 26, only one missing. So if it's limited in size, take advantage of it, put it down. It might make your confidence interval tighter, which is a good thing, but it will not hurt it regardless. Now, the example here is actually based off of GMAT scores. A GMAT, the Graduate Management Admission Test, is a score, an exam that you take typically to get into most MBA programs, and the score ranges anywhere from 200 to 800 points. Generally, the mean is 500, but different programs have different requirements for what it takes to get into their schools. And the standard deviation is always 100, so you understand where this data would be coming from. Let's see what happens if I made changes to any of this. You see here, what if I doubled the sample size? Instead of 25, I have 50. Notice what happened to the sampling error. I have the same sample mean, the same sample standard deviation, the same confidence level, but because I doubled the sample size, my sampling error got smaller. Now, instead of 550 plus or minus 41, it's plus or minus 27.7. Significantly smaller. And what if we wanted to be more confident? Instead of being 95%, we'll be 99% confident. Notice what happens. The margin of error jumped up to plus or minus 36. So more sure of yourself, you need more room for error. If I said, hey, how large of a target does a target need to be for you to be 100% sure you're going to hit it? You're going to want that target to pretty much be the entire room. That way there's absolutely no chance you can possibly miss it. Because if you have to be 100% sure, there can't be any doubt in your mind you will hit it. No doubt whatsoever. That would mean it has to pretty much encompass every floor, ceiling, and wall. It's impossible to miss. And that finite population size that's shown, well, if it's small in size, it could reduce your confidence interval. If it's really large, it can't hurt it. So if I have a population that's really small, my general rule of thumb is about 1,000 or less. It can help us to put that in. The population is, tens of thousands, millions, whatever. If you put in any number in that population size that's larger than 10,000, you're going to notice that the interval for an unlimited population is no different from that one. So may as well not even waste our time. But I'll show you what a difference it could make. Like before, you see what happens if the finite population size is 1,000. You see that instead of 550 plus or minus 36.428, it's plus or minus 35.523. A small difference, but a difference nonetheless. What if the population size were 51? Well, you've already got data from 50 people. You're only missing one. Since you're only missing one, whatever score that last person got, there's a limit to how much that person's score can raise or lower the average when you've already got 50 scores loaded. As a result, we know that it can't be off by that much. And so our margin of error has dropped down to plus or minus 5.152. Heck, if I put a finite population size of 50 down, notice the margin of error drops to 0. Why? Because we've got all the data. We took a sample of 50, and there's only 50 to get. So whatever we got from those 50 must be the truth. there no longer is a margin of error at that point. So yes, the population size, as it gets smaller, it should tighten your interval. And ideally, you would like to have the narrowest interval possible because your goal is to estimate the truth about the population. And you don't want that estimate to be all over the place. If somebody said to you, what do you think the average age in the school is? You don't want to be saying, well, it's somewhere between 10 and 90. And I'm 95% sure of myself. You want to have a much narrower interval. When pollsters are trying to predict who's going to win an election, it wouldn't do much good to say, well, we believe that candidate's going to get somewhere between 20 and 80% of the vote. Hardly useful information. They need it to be far narrower for it to do them any good. Let's shift over to proportion problems, and you can see it's very, very similar. While the mean problems had mean, sample size, standard deviation, confidence level, proportion problems, well, they don't have means, and they don't have standard deviations. They still have a confidence level, and then in addition to that, we ask what's the sample size, but then we also ask something about the number of successes. Now, in this case, success doesn't mean something good. It means that which we are tracking, counting, whatever. It doesn't matter if you're counting how many babies died at childbirth. If that's what you're counting, that is a success for our purposes. It's strictly whatever you're measuring, whether you're counting heads, counting tails, counting failures, counting success, whatever it is. Anything that you're counting is a success just for this purpose. So in this case, if you had flipped a coin and you expect the coin to be perfectly balanced, half heads, half tails, but if you flipped it 200 times and got 110 heads, that's 55% heads. The margin of error for that is 6.9%. So we're basically saying that if I flip this coin an infinite number of times, I would expect somewhere between 48 and 61.9% heads. Is that a bad coin? Well, it doesn't sound good, but realize it's a sample. And sampling error occurs, and you don't expect it to nail the 50% mark every time. The question you really ask yourself is, does the interval contain the 50%? Notice that the interval starts at 48% and goes to 61.9%. The 50% is somewhere in that interval. So I'm saying that if I flip this coin an infinite number of times, I expect between 48 and 62% heads. Well, a fair coin gets 50% heads. You have no reason to doubt the coin is fair. Just because it's leaning on the heavy head side doesn't mean the coin is unfair. It's a sample. Flip a coin 4 times, get 3 heads doesn't make it bad, even though there was 75% heads. So, yeah, it does lean heavily on the head side, but leaning that way, you don't turn around and say, well, it's almost significant or it's leaning that way. That would be like declaring a woman is almost pregnant. We don't do that. Unless the interval completely leaves out the 50%. So if I had an interval which started, like, look what happens on the next screen. I have, instead of 110 out of 200, suppose I flipped it twice as often, got the same results. I flipped it 400 times and got 220 heads. Still 55%. But now my margin of error is 4.9%. So I am now saying I am 95% sure that if I flipped it an infinite number of times, I would get somewhere between 50.1% and 59.9% heads. Well, both parts of that interval are above the 50% mark. I am saying with 95% certainty, 50% is not part of that interval, which means it's definitely not flipping it fairly. I am declaring that that is not a fair coin. Even if it's only by the slimmest of margins, it doesn't matter whether I miss it a little or miss it a lot. If the 50%, which is what I care about in this case, is not in that interval, then we would say, uh-oh, we definitely, we can then conclude with reasonable confidence, in this case 95% certainty, that that coin is not fair. Of all the questions I've ever been asked as a statistician, probably the most common one I've gotten is, how large of a sample do I need to take? Well, to answer this question about how large of a sample do I need, I often ask people 2 main questions. How much error are they willing to tolerate? And how sure do they need to be of this result? Well, now think about the typical corporate answer you'd expect to get to that. How much error can you tolerate? Of course they'll say, 0, I don't want any error. Even though that's not what we mean by error. And how confident do you want to be? Of course, they'll say 100%. I want to be sure. Well, of course, if they want no error and they want absolute certainty, I tell them, fine, sample everyone. No, we can't do that. There is no way to sample anything less than the entire population and expect absolute 100% accuracy. You're going to be off a bit or a lot. How much you're willing to be off by and how confident you are about that result is what's going to determine whether we have to take a really small sample or must take a really large sample or somewhere in between. The more error you're willing to tolerate, the less of a sample you need to take, and vice versa. The more sure you need to be of yourself, the more confident that is, the larger the sample you need to take. Now you notice nowhere in my questions did I mention anything about the population. It's a common misunderstanding. People think, well, you have to take a large sample if there's a large population. So if I said, what do you think is a good feeling sample size? I said, well, suppose that in a specific company there are 5,000 employees, and I sampled 500 of them. That's 10% of the company. Is that a good sample? Many of you would say, some would say yes. Many of you are questionable. Some of you say no. 10% not good enough. Even though we're lucky if 10% actually show up at election polls sometimes. How about if I had a company of 50,000 employees and I got 500 sampled? That's 1%. Is that good? How about the state, which has 5 million people in it, and I got a sample of 500? How about the country, which has 310 million people, and I got 500 people? You might think to yourself, oh my God, bigger population, I definitely need to get more people. You'll probably be surprised to find out it doesn't matter. 500 chosen from 50,000 is equally good to the 500 chosen from 310 million. It doesn't matter how large the population gets. I know that doesn't usually sit well with folks, so I have my own picturesque way of explaining that. Imagine that you are cooking chili for your family, and you like the 5-alarm type of chili, really hot and spicy. You got a big family, so you make this 2-gallon pot of very spicy chili. And you're stirring it, and, every time you have a chance, turn the heat down, do whatever, but you're stirring it. And then you get a call from Grandma. She's coming over, but she can't eat anything that spicy. That's okay. You still have some ingredients left over, so you make her own version of non-spicy chili, of no-alarm chili. Hey, but you don't have to make that much of it, so you put it in this 1-quart pot. So you got a 2-gallon pot of the really spicy chili and a 1-quart pot of mild chili. You take your spoon out, you stir both pots. I say, well, let's see if they're ready. You take the spoon, you dip it into Grandma's chili. It's perfect. How many spoonfuls of the big chili would you have to take now to figure out if it was ready? Would you have, now since there's 8 times as much chili in the big pot, would you need 8 spoonfuls? No. 1 spoonful will suffice. 1 spoonful tells you as much about the big pot as it does about the little pot. And how is that possible? Simple. We stirred the pot first. By stirring the pot, we mixed the ingredients in there so they're homogeneous, essentially. Once they're like that, it doesn't matter whether I take 1 spoonful or 8 spoonfuls, they're equally good and representative. That's the key, is the data must be representative. So we get fooled into believing we must have a really, really large sample. You'd be surprised to find out the Gallup poll is often only about 400 people. The Nielsen ratings are based on 1,000 homes nationwide. A lot of polls that you see are only based on 400 to 500 people, and they do quite a good job of predicting, providing that it's not rigged and the sample truly is a good sample to begin with. So let's look at an example of how we would calculate the sample size. If you go to the spreadsheet for sample size calculations, once again we're using GMAT numbers here. We would say, well, we know the standard deviation is 100, And if I said, I would like to know what the mean GMAT score is at our university, but I'd like to know it within 25 points, and I want to be 95% sure. Well, the formula for calculating the sample size involves a couple pieces of information, just like with confidence intervals, because these two are related, because one is really an inverse of the other. To figure out that sample size, I need to know the three things you're looking at: the confidence level, the sampling error, and the standard deviation. And the role each of them plays, well, if you want to be more sure of yourself, you'd better take a larger sample. So if I said, hit that target, throw a beanbag at a target, and I want you to hit it. And if I said, I want you to be 90% sure you hit it, how many throws will you need? If I want you to be 95% sure you're going to hit it, how many throws will you need? You're going to need a lot more throws if you want to be more sure of hitting it. The sampling error, well, if you are willing to be off by a lot, you don't need as much data. If I said guess the mean score within a couple hundred points, it doesn't take that much data to be within a couple hundred points. If I said guess the mean within 1 point, you better sample a whole lot of people to be that accurate. And then the standard deviation. Well, if the standard deviation is only like 5 and you said I want to be within 25 points, when you consider the standard deviation is only 5, you're giving yourself a wide berth there. But here we have a standard deviation of 100. So we have a much wider spread of the data to begin with. We're saying naturally 2/3 of the data is plus or minus 100 points. That's a pretty big spread, and I'm trying to get the mean within 25 points. So putting those three pieces of information into the formula, we get a minimum sample size of 62. We could certainly sample more than 62, we just shouldn't sample less. What if we were willing to tolerate more error? If you go to the next screen, you see what happens if I change the sampling error from 25 to 50. The sample size needed changed to 16. We're saying that with only 16 people, we can estimate the average within 50 points and be 95% sure of doing so. Now, what if you wanted to be more sure of yourself? Well, if you want to be 99% sure instead of 95% sure, you're going to see that the sample size needed is going to go up once again. In the next screen, you see what happens if we increase our confidence level. If you want to be more sure of yourself, you notice the sample size does indeed go up. Well, now let's take a look at what happens if we said we want to be 99% sure of capturing the true mean within 40 points, and our standard deviation was 100. The output table here shows a sample size needed of 42. Well, what does that really mean? Let's go back to the confidence interval screen. Using the standard deviation of 100, doesn't matter what sample mean we use, let's just pretend the sample mean happened to be 550. Plug in that sample size of 42 and the 99% confidence interval, which is what we were going after, and notice the confidence interval itself is 550 plus or minus 39.746. It's within the margin of 40. Our goal was to get a sample such that the mean would be within 40 points. We wanted the interval to be no larger than 40 points. So that's why we do these sample size computations, is to figure out what that optimal confidence interval is. So we're saying, how large would a sample would I have to take so that my confidence interval will be no bigger than plus or minus 40? The answer, take 42. I took 42, plugged it in, and lo and behold, my confidence interval was less than plus or minus 40. And I guarantee if you changed the sample size down by even 1, dropped it to 41, your margin of error would go above the 40. That was the absolute bare minimum that you needed to guarantee that your interval was exactly what you wanted it to be. You could have gotten to that information by trial and error, but this gets you there a whole lot faster. Pollsters use this all the time. We want to be able to predict who the winner is within 3 percentage points. How large a sample do we need? That's the reason they'll do that. They want to know how many to get so that they didn't get results and say, My God, it's give or take 7 points. What good is that? Go get more data. Go back and do it again. They want to know up front what they will need to get the answers that they need for their questions. Now let's skip over to the sample size for proportions. It's very similar to the sample size for means, except, of course, there are no standard deviations here. And there's something here called the estimate of true proportion. With an asterisk there, it says to use 0.50 when unknown. What that's about is sometimes in trying to estimate the sample size, it's something we know nothing about, and that's fine. But if it's something we have historical information on what we expect the results to be, put that in. Now you might think, why would I put something in if I knew what it was supposed to be? I wouldn't be doing this in the first place. Well, we understand that. It's just we know things change. But if you have a ballpark idea of what it should be, and it's not around 50%, putting something else in there can often reduce your sample size dramatically. So if we said, well, we want to know how many people should we survey so that we could figure out what percent are voting for X, and we want to know within 5 percentage points, and we want to be 95% sure. Based on those pieces of information, we would say, sample 385 people. You sample 385, you will get the results you're dreaming of. If we had historical information like, well, we know that when we poll people in this particular district, like, for example, in D.C., when every election comes around, you could pretty much count on at least 87 to 90% voting for the Democrat. That's pretty consistent. Based on that, if we have a pretty good idea and you put a number in there other than 0.5, it can only reduce the sample size. Any 0.5, it forces it into the highest possible number. Any number greater or less than 0.5 in either direction, as you get closer and closer to 1, either direction, it will reduce the amount of sample you need, which is a big help. So if you say, well, I expect it to be like 90% Democrat and 10% Republican, you might find that you don't even have to survey 100 people. And if you don't have to survey 100 people, that's great. You're saving yourself a lot of time. You're saving yourself a lot of money. And when the results start to roll in and you go, we got the first 100 votes counted, and it's 93% for the Democrat, 7% for the Republican, I think you can shut the polls down. We feel pretty good about the results. But when you have places where we expect the results to go down to the wire, we're going to need larger samples. The closer the results would be to 50%, like in the last elections, Florida and Ohio and a couple other places, the results typically come out right around 50%. The closer you are to 50%, the more data you need. You're not likely to declare a winner in one of these battleground type states unless you have a lot more data to base it on. So the less information you have, heck, just go ahead and say, I'll use 0.5. It can't hurt. And same rules as with the mean apply here. The more error you're willing to tolerate, the less sample you need. The more confident you need to be, the larger sample you need. Beyond that, they're pretty much the same. That wraps up our unit. The next unit will begin hypothesis testing. That's where we really delve into inferential statistics. And everything we've done up until now will really come in handy. It's definitely interesting. You're going to see this is a topic that's very commonly used in everyday life, only you don't know that you're doing hypothesis testing when you make decisions.